Alright, so in this video we're just going to work through some examples of solving some differential equations by complexification. And so here's our example. Um, y double prime plus 9y equals sine of 3t. Okay, now in this case you might notice, right, that our y sub h is going to have roots that are plus or minus 3I, and so that is going to give me a problem, right? So then when I guess my particular solution, I'm going to have to multiply that by t. Okay, that complicates things a little bit. Yp prime then is going to be, um, well, we just need to use the product rule here. Okay, so that's going to be 3I times t a e to the 3it. Then yp double prime. And again, just use the product rule here where you'll have the 3i times a e to the 3it. 3it. Then we'll have a 3ia, so that's going to actually be 6 of these. Plus, and then the last one will be minus 9. Oops, so I guess I don't need the plus sign. Minus 9t ae to the 3it. Alright, and so now we plug things back into the differential equation. And what do we get? Just drop that one out. Add these, let's see, I'm going to have 9 times y. And what do you get? The t's cancel out. And you're left with, let's see, sine e to the 3it on this side. I almost wrote down sine. And then on this side we have 6i times a e to the 3it. Right, and so the 3 e's cancel, and then a is equal to 1 over 6i. Good. And notice that that is, if I multiply by I over I, right, minus 1 over 6 times I. Good. And so now we want the y sub p is going to be the imaginary part of ate to the 3it, right, because we started with the sine function instead of the cosine. And so that's going to be the imaginary part of minus 1/6 I times t cosine of 3t plus I sine 3t. And are we able to read off the imaginary part from here? To get the imaginary number, I'm just going to be multiplying this times this, right? And so that'll just be minus 1/6 t cosine of 3t. Very good. All right. So that is what you do if you run into a sine forcing function instead of a cosine. Good. Now, I want to set up the general form of the shortcut that we had last time, just so you can see how that works. I want to just run through that one more time before we finish the section. So I'm going to pause for a moment and write down the first couple of issues. Okay, so we're solving the second order generic differential equation here. So notice I've got a p and a q there instead of the usual a, b, and c, just so we don't have to deal with that first constant. I plug in my guess, my ansatz for the differential equation for the particular solution, and then I plug it in. And what do I get when I do that? I'm going to go ahead and factor this out, and then I'll have a minus omega squared plus p times I times omega plus q equals e to the I omega t. And then we cancel the e to the I omega t's, and then we get a is equal to 1 over q minus omega squared plus I, usually we write the I by itself there, times p omega. Good. And so what we said was that for the shortcut, we can write a shortcut for y sub p now is to write as r times cosine omega t minus delta, where r is equal to the square root of, actually, let me rewrite that as 1 over the absolute value, or the magnitude, of q minus omega squared plus I times p omega, and delta is the argument of this complex number, which is q minus omega squared plus I times p omega. All right, and so if I want to rewrite that, this would be this 1 over the square root of q minus omega squared plus p squared omega squared, and then delta, I'm not going to simplify that any further. Okay, now we could prove this, but it's really just algebra. And what is the algebra? The proof here is what you would get if you multiply a e to the I omega t out, and then take the real part, and then write that as r cosine omega t minus delta. Okay, so you see that that's not really complicated. Oh, something's done. But it's not complicated, but it just takes time to do. So we'll do one more numerical example using this idea, just so you can see how nice it is when we have this shortcut. All right, so here's our differential equation. We'll solve for, and this again is just for the particular solution, when we're given y double prime plus 3y prime plus 2y equals cosine of t. Oops. All right, so therefore our ansatz is y sub p equals a e to the it. Yp prime is I times a e to the it. Yp double prime equals minus a e to the it. Plug those into your differential equation and factor out the e to the it. Minus 1 plus 3i plus 2 is equal to e to the it. Good. So the e to the it's cancel. A is equal to 1 over 1 plus 3i. And we're pretty much done at this point, because now our y sub p is going to be, well, let me rewrite that. The r in our expression will be 1 over the magnitude of 1 plus 3i, which is 1 over the square root of 10. And our delta will be the inverse tangent of 3. And that is in the first quadrant, right? So I don't have to worry about adding pi. Very good. So therefore, the particular part of my solution is 1 over the square root of 10 times cosine of t minus delta, which is the inverse tangent of 3. And we are done. Easy. Easy, easy. All right. So you'll notice, by the way, that I didn't memorize these formulas. I was really trying to get to this point, right? Because once I have this value of capital A here, I can read off my complex number, and then everything else is done, right? So that's how you do it. This is a really nice shortcut to know for section 3.8. I know we're doing 3.7 next, but you might keep it in mind. There's some practice problems in the handout that summarize all the stuff that we just did. All right, see you later.